I think so. We will continue from last time class. So I think I want to explain you and discuss with you about the F number and numerical chart and photographic image. So how many of you are interested in photography? Raise your hands. Interested in photography? No? Okay, as far as you guys are taking this class, I hope you guys should be interested in not only microscopy, but also photography as well. So you see this one I showed you. So 1/125, and that is, I believe it's a camera shutter speed, and f5.6. So this is so famous for F number. Now we are getting a little less and less, but so you guys who are interested in photography, Jungmyo, I took it from your desk. Okay, so these microscope, not microscope, camera lens actually have this, and if you look at close on the side. So let me show you one example. So look at through. So let me change this shutter F number. So when I change, you see this is big. It's a small F number. When I make it higher and higher, bigger F number, you see the aperture gets smaller. So I hope you can see these differences. So let me see if I have f2.8. Let me check f2.8. This is 2.8. So you see the size, relative size of aperture. Let's say I want to go to F number of 16. Let me try to go to 16. Look at that, how tiny that aperture is. So that's what it is about F number, and that's a very important concept for us. So what are the changes and differences between this F number of low one? I think the lowest one is 1.2 here. So in that case, this is the image you can take. So you see somehow it says more light. I guess it's some very shallow place. You have a sharp focus, especially the focus, but out of the focus, you see all blurring happens. Compared to this high F number, let's say F11. So F11, if I go to F11, so this is F11, and this is the image. Actually, this is more closer to your smartphone lens because it has a smaller aperture size, and you have, of course, less size. So overall, this is darker. But you notice is, look at every plane, you can at least kind of see things. So this is useful for like smartphone application. You don't necessarily consider about any focusing. Okay, so then, yeah, if you are a camera developer or lens designer, how would you define your parameter? So let's try to come up with an idea for how to define F number. That F means like focus. So of course, there's a lens. Your camera lens, you can consider as a one lens, and there's going to be a focal length. And another parameter you can actually think of is the aperture diameter. So this is in fact a aperture stop, right? So you just have the ratio of focal length and aperture diameter. So let's say focal length divided by the aperture. This is diameter. And let's define as an F number. So what does that mean? If F number is big, relative focal length is usually fixed. So if F number is big, that means the aperture size goes down. So remember, big F number, aperture size smaller, smaller F number, and your aperture size is big. So does it make sense to you? Yeah. One thing it's a little confusing is F/number. So this is, you can consider as just one parameter of we call F number. Okay, so that's why we sometimes just put it F/ just a number pound. Okay, pound notation. So in fact, you learn about numerical aperture before. So numerical aperture, this F number, roughly you can consider because numerical aperture is defined not just diameter, but half the radius and the angle of half the angle. So in fact, F number is almost similar to 1/2 numerical aperture. So that's what you can consider. And just sometimes confusing is we sometimes write down like F number F/8.0. Let me, so what this means is F number equals 8.0. So that's kind of nomenclature we are using. So with that, I think we want to understand what does that mean, that if we have a smaller F number, that means it's defined by focal length divided by the diameter. When it goes down, so for example, like F of 2.8 or smaller one, that means is a numerical aperture is actually getting higher. And as I say, numerical aperture can be approximated by this. In fact, it's like paroxial approximation angle. And what about entering light? So smaller F number means a bigger aperture diameter, so you will have much more light, because the amount of light matters about the signal and the brightness of your image, and even shorter your exposure time so that you can take much faster movies. And the other aspect is actually depth of field. So smaller F numbers such as like this, you will inevitably have a shallower depth of field. In comparison, if you have a high F number, you will have long depth of field. That means you will be virtually focusing on many depths. Okay, so which one do you prefer? I think it depends on your purpose. Like smartphone, you just don't want to focus like each plane, so you want to have all through a nice focus like this. However, if you have some artistic sense, you're a photographer, you want to focus just the right plane, and then you just blur out in and outside of the focus, so you can focus, make the image much more interesting. So that's what the depth of field in artistic sense. But at the same time, it's important for lower F number or bigger aperture at the same time means resolution. In fact, today's class is exactly about this. So we will discuss this one soon. So let's go back to a little bit more practical, that immersion oil case. So increasing NA and resolution is today's topic. And I'm getting started with just formula first. So numerical aperture is defined by the sine theta max multiplied by the medium refractive index. So that refractive index is there. It can be, it's usually the same or bigger than 1. So that means you can increase NA and you can increase resolution. That's why we sometimes utilize immersion water or oil. Okay, oil has even higher refractive index than water. So this picture actually shows a schematic of, in fact, the information of the light, which has to pass through the subjective lens. So this is just a cartoon. Don't consider it as a scaled one, but you want to see things, let's say, from the sample. These red lines are the light emitted from the sample. But remember your Snell's law. Glass has 1.52, while air has 1. So you have to go a little bit outside of this angle. What that means is, as it goes higher, you start to out of the optical system. You cannot take that information anymore. So that's a shame and problem, because you're losing your information. So for that, one quick remedy for this, just pour oil in this space, okay? Then the cover glass and this index matching oil allows you to take all these rays information entering into your optical system, and you get a better information. So that's immersion oil, the role of immersion oil. So that's index matching with cover glass. And if you have a laboratory, look for the index matching oil. Okay, so one question about for you is, hey, wait a second, you can ask question how to increase your numerical aperture even further. Then, okay, so rays coming out this, what about rays coming out even higher and higher angle? If you could capture that, that would be awesome. So of course, for this industry already made that as a like even hemispherical lens in front of it, so that you can capture as much as possible and bend it through into your objective lens. So this is what we call SIL, or solid immersion lens. Okay. And for those who haven't used oil immersion objective lens, so I really want to give you a real sense of what it is look like. So I guess in my class, you guys have not used oil immersion. So look at this objective. So when we use oil immersion, that means the immersion of refractive index is 1.5. That means you want to have extremely high numerical aperture, such as 1.25, 1.4. Then usually must having oil immersion. Okay, that's your objective. When you remember on the side better of your objective, you will find a WD, or working distance. And in fact, this one has a WD of 0.23. What that means is only 230 micron is your working distance. Think about that, how small that is. It's less than a quarter of your 1 millimeter. So your eye is virtually touching the cover glass. And the nominal standard cover glass thickness is also very thin. That's 170 micron. And underneath, you will put your thin sample there. And of course, you have a microscope slide, which is about 1 millimeter thickness. So this is what you are seeing. So think about this. You have an extremely expensive objective lens. You have even more important sample at your, like you made over several nights, okay? And you just put it there and then try to focus a break. You can break your sample, and even worse, you may break your objective. That's the worst thing ever happened. So you gotta be super careful. Always the rule is you put your objective as close to your sample, always turn the knob the way away from the sample while you are focusing. So that's the practical tip you should have. And I think this is extremely important when you are dealing with your actual samples. Now, I want to discuss, previously I also showed you a condenser, substage. Condenser is for image contrast and optimal resolution. So let me bring this picture, and also condenser lens. In fact, you remember that this is a substage condenser lens. And actually there's a one filter over here. That is I think this is IR blocking filter. So let's see. So you have everything ready: objective, specimen, microscope slide, and you have this ABE, like in this case, two lens condenser, you have aperture diaphragm. So condenser is really like you are with high magnification, you are really seeing very tiny, small area of your sample. So you need to bring enough light. So gather light from light source to eliminate specimen. Even not just, you don't focus your light onto your sample. Okay, you want to have uniform intensity over the entire view field. What that means, remember last class we discussed about queller illumination, because you want to uniformly illuminate your sample. Okay, so how do you adjust your aperture of your condenser? That it's very simple, because your objective has the angle of acceptance, which is defined by the numerical aperture. You want to match condenser NA to the NA of the objective. It's very common, you can think of, because otherwise, if you shine more high angle, that light would not going into your system, okay? An image of the diaphragm is at the same location as image plane of the objective lens. So that's a aperture diaphragm. All right, so as a last part of the microscopy, I want to discuss briefly about light sources. So you know which one would you like to choose for your shining. So this is a commercial microscope. You can typically see in this is called the inverted microscope. What it means is objective lens is looking above. So that's inverted. If the other way is in upright microscope. Okay, so in this case, usually tungsten halogen lamp housing is from the top because you want to use it typically transmission illumination. However, normally when you are dealing with fluorescence is typically epifluorescence, so that from the same side of the objective you have this housing that is mercury or xenon and metal halide. These will come into here as a epi illumination. So what I mean by epi illumination means epi is on top. So you are shining the top of the sample and looking at the sample from the same side. This is inverted microscope, so it can be a little confusing, but what that means is the imaging side and shining is from the same place. So now we are banning the use of mercury arc lamp, mercury lamp, because mercury is actually bad for health. So in hospital environment, now we are getting less and less use, but I used to use this one a lot. This one only lasts for 200 hours, but it's expensive. I think one is about $200. So I use it until, like it says 200 hours, but we use it until like 400, until like it flickers. Okay, this is gonna be dangerous. Now I don't want to use it. I want to replace it. Okay, and the other one is xenon arc lamp. This is also very expensive, and you look at this is kind of making arc, and they generate the light, candela per square centimeter. And now things are moving towards a very cheap and more robust light source, such as light emitting diode or LED. This, the LEDs are everywhere. Even car headlight is like being replaced by LED. So it's actually versatile, cheap, and actually my room, the light is also replaced by LED. So that's great. However, if you look at inside the LED, these lights coming out here, actually it's not like point source. It has some pattern in it, like a filament in this lamp. So you gotta be careful a little bit when you use it. And further, when you are having a fluorescence microscope, or you have this research facility microscope that is a very good commercial fluorescence microscope, you will realize their light source is usually now replaced with a metal halide lamp house. So that looks like it. This is also arc discharging with a nice reflector. And you see there's a thermal filter there. So this thermal filter blocks the IR light, because IR light, when it hits the sample, it tries it's kind of hitting the sample. You remember the absorption of biological tissue with a longer wavelength, there's a higher absorption with water. So you block that one with thermal filter. And in this metal halide, you have this nicely designed elliptical reflector, which focuses down to couple your light into the liquid light guide, so that it can be a little flexible. So you have now nice liquid guide, which is just plug into your microscope here, that will work. So you look at this LED and xenon lamp, they don't have those, but metal halide, the cool thing about this is it's more expensive, but you see this nice liquid guide, which is flexible. So that makes your life much easier. I would say these days, even LEDs, we designed that one. So we also use like liquid guide for LED as well. So the question is when to use and why do we use? I guess price-wise, LED itself is pretty economical. Metal halide, I think this is about $3,000 per this lamp, but compared to this $200, but this one lasts much longer. Okay, not forever. That's the difference. Okay, so then you will ask, why not LED for everywhere compared to metal halide? And here you have to think of the spectrum. Okay, so U shining tool. So this picture actually shows what to choose. So in fact, what's important is on this color scale, wavelength, and spectral intensity. You can see mercury lamp. The reason why mercury lamp was very prevalent before it's you can see there are peaks here: 365, 405, 436, 546, 579. So mercury has a nice peaks out there, which you can actually choose your typical fluorescence samples there. And sometimes you will realize, for example, in neuroscience, people are trying to do some fluorescence lifetime. So some of other applications, mercury has only a defined peak. So what about I have a fluorophore which has to shine in here and it's very low for mercury. So that's not good. So because of that, if you need a more versatile illumination over this wavelengths, you can see xenon arc lamp provides quite uniform, not like super bright, but quite uniform illumination spectrum. So that's when you have to use xenon, and this is also very expensive. And interesting, metal halide also provides very similar to the mercury arc lamp, but it doesn't have mercury, which is a heavy metal. Once it's broken by accident, it's bad. The gas is bad for you to intake. So that's why we are replacing this. And your like home tungsten halogen lamp or typical pathology microscope uses a relatively cheap like tungsten halogen. And the good thing is this one also you can see this a nice throughout the wavelength of all the visible, it provides a nice illumination, but you can see it's higher and higher. So that's why you put, actually this is tungsten halogen lamp I showed you. I think you see this filter, you can see that is actually this heater filter. So it blocks IR. Okay, you will ask, hey, what about LED? That's cheap. Well, that's nice. Why don't we use it all the time? Very good idea, but you have to know the LED spectral profiles. So LEDs usually have this kind of shapes. So you can buy a number of LEDs from any shops or Thor labs. You will be able to identify depending on your need. However, LEDs have only defined one. So you don't have like the whole range LED. So that's the issue. If you know exactly, let's say you are using GFP or green fluorescent protein, you may want to use 465 or 505, something like that. So that maybe 505 might not be good. If you look at the spectrum, it goes a little too broad, so you cannot block it compared to GFP. So you want to use 465. So that one gives a nice 465 and gives about less than 500. So this would be good. So in that case, you need to have multiple kinds of LEDs. So even single LED is cheap, but you need to have multiple LED and you have to control it. That part makes it a little more expensive. So that's what you have to know. However, it's very durable, okay? So here, this is a table. I mean, this one is for your reference, okay? So you can compare like, hey, you always think of like you are initiating a new project, a new experiment, or you become a PI and you have to make your own lab. So where do we get started? So you have to think of halogen, mercury, xenon, metal halide, and LEDs. So you can think of this comparison. But remember, tungsten lamp is 100 watt, like mercury 100 watt. Wow, that's very, very high. Why do you need it this high? Because you cover a lot. Okay, so in fact, what matters is spectral irradiance. That means within 1 nanometer of a spectrum, how much light you are actually generating. So in that regard, this 100 watt, there's a lot of heating and you are actually not that efficient. So when you are designing your experiment, you have to consider your wavelength characteristic, your brightness, and also stability, coherence, and uniformity. Okay. And LED, of course, is an emerging technology. And in our lab, we also have LED like 3 color, 4 color, 5 color. And however, one thing I have to make you understand is, you know, there are like typical white light LEDs. It sounds good because it's white light, but in fact, the white light LED is usually a combination of a yellow LED plus blue LED. So it actually is a little weird spectrum. If you look at the spectrum, like there's a peak in the blue and then like gross yellow part. And that combination gives us kind of yellow, white light, but you have to think it into spectrum aspects, okay? So that's a little different from typical sunlight based. All right, so to finish this one, I actually put this a Barry Masters kind of article for Ernst Abbe and Foundation of Scientific Microscope. So this is rather old, but it gives a nice historical context for the early development and the development of limit of optical resolution. And I already shared this one, microscope basics and beyond. This is such a well explained one, so you should have it. Whenever you have a question, you can actually go back to here. All right, so that's the summary, history, histopathology, bright field microscope. Now I think we're going to diffraction theory and optical resolution.